Okay, good morning everyone. Let's get started. So we finished 2 chapters, that is the review of governing equations and overview of numerical methods over the course of the past lectures. These were very short chapters. Okay, it was kind of an overview and the review of governing equations. So we will move on to the third chapter, which is relatively takes a while. So that is the finite volume method for the diffusion equation. Okay, so this is third chapter, the finite volume method for diffusion problems. So we have kind of visited this part during the overview chapter, right? So we are going to kind of redo some of these stuff with some emphasis on the source terms and the discretization and things like that, and then we will depending on the time take up one problem that is in one dimensions and try to solve, at least get the discrete equations. Okay, so that is the agenda for today's lecture. So in order to get the diffusion equation, we start off with the general scalar transport equation. That we have derived earlier, that is partial t of rho phi plus del dot. Do you remember the equation? What would the convection term look like? I would del dot rho u bar phi, okay, equals, on the right hand side you have the diffusion term, that is del dot gamma grad phi plus some s phi, right? So we have a unsteady term and we have the convection term and we have diffusion and a source term, right? So we have these 4 terms. So essentially, in order to come up with a diffusion equation, we just have to set the unsteady term and the convection terms to 0. Okay, so we are going to set the unsteady term to 0 as well as the convection term to 0 to arrive at a steady diffusion equation. Okay, which is now has only 2 terms remaining, that is the diffusion term and the source term, and the left hand side is now 0. So we can write this equation as del dot gamma grad phi plus s phi equals 0. Okay, so this is our steady diffusion equation, which is going to be the equation throughout this entire chapter. Okay. Of course, we will add the unsteady term little later in the chapter, and we will look at discretization from 1D, 2 dimensions, 3 dimensions, and on structured and unstructured meshes. Okay, fine. So let's move on. Let's look at a 1D diffusion equation. This will be kind of a recap, but with few items embedded in there. So this will be like a one-dimensional diffusion equation. Okay, so we already saw that the first step is to integrate the governing equation on a control volume. Okay, so if I were to write a 1D equation, that would read del dot, let me first write it the 1D form. So essentially d by dx of gamma d phi dx plus s phi equals 0, and we would write it in a little more convenient form, that is del dot I gamma d phi dx, right, plus s phi equals 0, so that we can apply, so essentially we can now integrate this equation on a control volume. Okay, so we are going to choose a discretized a domain, that is we are going to choose a mesh that looks like this. These are the, let's say, the interior cells. We call the primary cell P and the cell to the east as E and to the west as W, and the faces of the P cell we are going to call it as little e and little w. Okay, and we also indicate the distances. Let's say this width of the cell is delta x, and the distance between the centroids of the P cell and the E cell we call it as del x e, and the distance between P cell and the west cell we call it as del x w. Okay, so we have this kind of notation. Now, so the control volume we are focusing on is this guy. This is the control volume. We will integrate our governing equation on this control volume as integral control volume del dot I gamma d phi dx dv plus integral control volume s phi dv equals 0. Okay. Let us also assume that this is a 1D problem. Let us also assume that the area of these faces, of these east-west faces, is has a magnitude A. Okay, and if we were to write the vector, that will be A bar. Okay, so the area vector is A bar and has a magnitude A. Fine. Okay, so now what would be the next step once you have integrated on a control volume? What do we do in the finite volume method? We essentially invoke Gauss divergence theorem and convert these divergence operator into the volume integral into a surface integral. Okay, so we are going to invoke the Gauss divergence theorem. Okay, so apply Gauss divergence theorem and arrive at, essentially convert the volume integral that we have here into a surface integral. That would be integral control surface I gamma d phi dx dotted with dA bar plus we leave the source term as it is. This is s phi dv equals 0. Okay. Now, now we are going to replace this integration with a summation. Okay, assuming that the faces that make up the control volume are all planar surfaces. Okay, so these are all planes, and this particular value that we have, gamma d phi dx. Okay, so the gamma d phi dx remains the same. Okay, kind of remains the same, or you can have a remains the same over the entire face. And we can essentially the phase centroid value, that is the gamma d phi dx evaluated at the phase centroid, we call it sub f. Okay, the phase centroid value prevails over the entire face. Okay, so that is the assumption we make. As a result, I can replace this continuous integral, okay, with a discrete summation, okay, summation on all the faces as I gamma d phi dx dotted with A bar. Okay, now these are all for all the faces. Okay, so then this quantity has to be evaluated on the face and this will be on the face. Okay, so that is what we have. And if we go back, how many faces do we have for our cell? We have only 2 faces. Okay, this is kind of a 1D problem. So we have east face and west face. So this summation has to be done on f equals E and W. Okay, little east and little W, plus I am going to again say that we can replace this s phi dv with a cell centroid value. Okay, so we have some kind of an average value which is denoted with S phi bar. Okay, again this is evaluated at the cell centroid. Okay, and then we multiply with the delta V, that is the volume of the cell. Okay, S phi bar delta V. Now, what are the area vectors that we have? A east is what? A east is facing in the positive x direction. If we were to denote our x axis in this direction, what would be A east? A east is this way, right, and A west would be this way, right. So this is our A east and this is our A west. Okay, if we were to write A east bar, okay, so this would be how much? This would be I A little e, right. So where A east bar is the vector, A e is the magnitude, and A west would be minus I A west, right. A west bar would be minus I A west. Of course, I am using this east and west subscripts, but we know that all are the same, right. A east equals A west equals A. Okay. Alright, then I am going to substitute for these. So, A east would be A east bar is nothing but I A east, and A west bar would be minus I A west. Okay. Then if I evaluate this, what we are going to get is gamma d phi dx on the east dotted with A bar plus gamma d phi dx, I am sorry, it should be in I here, I dotted with A west bar plus SV bar delta V equals 0. Okay. Now, if we plug in what is AE bar as IAE, we are going to get gamma east A east d phi dx evaluated on the east. Then from the second product, that is A west bar would be minus IAW. So, this would give you a minus, which would be minus gamma west A west d phi dx evaluated on the west face plus SV bar times delta V equals 0. Okay, so far so good. Now, we obtained gamma and the gradients on the faces, right. All these things, the gamma and the gradients d phi dx needs to be evaluated on the faces of the control volume. Okay. Then assuming that we only know, let us say we only know the diffusion coefficient on the cell centroids. If we know gamma only on the cell centroids, that means we know gamma values on the gamma p, gamma capital E, gamma capital W, then we need some kind of an operator to calculate what would be gamma on the faces, right. That is what would be gamma on the little e and gamma on the little w. Okay. Assuming that let us say we have a uniform mesh, the easiest thing would be to do a linear interpolation, right, and obtain the values of the gamma on the faces from the values of the gamma on the cell centroids. Okay. So, I could just write what would be gamma east as gamma p plus gamma capital E upon 2, and gamma west would be gamma p plus gamma w upon 2. Okay. Now, we just used linear interpolation. And if you use a linear interpolation like this, then this is called central differencing, okay, in the context of finite difference methods. Now, we are not saying whether linear interpolation is the right thing to do or not. Okay. As of now, we are saying if you have a uniform mesh, we could obtain the values of the properties on the faces from the values on the cell centroids using linear interpolation. Okay. So, this would be a discussion for another day, where is this correct or not. Okay. We will follow up later. Fine. Now, somehow somebody has given you the gamma diffusion coefficient on the cell centroids, you know how to calculate on the faces, and you would use those values right here in these equations. Okay. Now, A east, A west is also known. Now, again we know that we need to evaluate d phi dx and d phi dx on the east and west faces. We said again we would use a linear profile assumption for the variation of phi, okay, with which we can say that we can approximate d phi dx on the east face as phi capital E minus phi capital P upon del x E, right, and d phi dx on the west face as phi P minus phi W upon del x W. Okay. So, we have these two linear profile assumptions with which we can evaluate the fluxes on the faces of the control volume. Okay. Alright, so far so good. Now, if we go back to the equation, we have the SV bar term. Okay. So, we have SV bar. So, in most practical applications, SV bar is basically value of the source term evaluated at the cell centroid. Okay. So, this is basically value of source evaluated at the cell centroid, okay, at cell centroid of P. Okay. Now, this would be a nonlinear function. Okay. In general, this would be, in general, this source term could be a function of the dependent variable. Okay, so that means this could be a function of phi itself. Okay, the S phi that we have could be a function of phi, or it could be constant. Okay, or it could be a nonlinear function of phi as well. Now, one assumption we make here is that we have to linearize the source term. Okay, so that means what we are saying is, let's say we give you an expression. Okay, I give you an expression to you as S phi as some nonlinear function of f of phi. That means, let's say this is some phi plus phi square plus phi cube or something like that. Okay, with some constants in the front. Now we cannot use this form directly in the discretized equations. Why is that? Because the small changes in phi would result in a very large changes in the source term. As a result, the solver you are going to use may not work. Okay, it may diverge. Okay, as a result, we have to linearize the source term. Okay, and if we say linearize, that means S phi can be at most a function of phi to the power 1, or it could be a constant. Okay, now again this will be how do we linearize? How do we linearize S phi? This is again a topic for another day. Okay, we are not going to discuss it now, but as of now I am going to give you a linearized model. Okay, will the linearized model work or it will not work? All these things we will discuss on another day. Okay, as of now you would take it for granted that given any source term, we can linearize it to be evaluated the cell centroid as some constant plus, that is S sub c plus S p, okay, times phi p. Okay, so essentially this is to the power 1, right. So this is a linear model. So this is a linear model, okay, which I have approximated. Okay, this is a linear model for source term. Now, one question that pops up in your mind is that, okay, you have just changed a big nonlinear function into a linear model, do I get the same result, right? Because we have changed the physics. You will get the same result in the end when everything starts converging. Okay, it only changes the path to the solution. Okay, so that we will see later on. We will justify that it will only change path to the solution as long as we are going to recover the same source term once you reach convergence. Okay, so that we will discuss in some other lecture. Yes. Okay, so the question is about the way in which we have written the fluxes, right? The phase fluxes d phi dx on east and west. Y is essentially phi p coming in the as a minus here, and y is phi p coming in the positive here. That is to do with the linearization, right? Essentially, you have a linear profile. So if you essentially write delta x e as what? X east minus xp, right? And this as xp minus x west, then you would get this as phi p minus phi w, right? It has to be always between 2 points, right? And the points happen to be 1 and 2 and 3, right? Essentially, you have west p and east, right? The question is, let's say I have some value, this is phi east, some value phi p, another value phi west, and these are at different x locations, right? So this is x west, x p, x capital E. How do you write a linear profile assumption? How do you calculate the slope? Phi east minus phi p by x east minus x p, that will give you positive here, and similarly you would calculate the other slope as phi p minus phi w upon x p minus x w, right? Or if you want to write it phi w minus phi p, then you would get a minus in the denominator. So because we have taken away that minus with the delta x, right? So delta x is always positive, as a result the numerator changes, right? That's all. We calculating what is the value of this slope at the midpoint, that is on the east face and on the west face. Now it need not. So the question is, we are not assuming that phi is increasing. Phi could decrease as well, right? It is how do you calculate some change in the numerator, let's say some change in delta u by some change in x. This is always between 2 points, right? You would write this as u2 minus u1 by x2 minus x1, or you will always write it as u1 minus u2 by x1 minus x2, right? You cannot change the points, one for the numerator, one for the denominator, right? That's what we are doing. So it need not increase this way. So you could even have your variation of phi as it could even go this way, right? It could go in any way, right? The definition remains the same. So essentially what I have drawn here is for different locations. So we have, let's say, phi west, phi p and phi east. It could be even this way. That you can check, okay? That you can check later after the class. Other questions? We are only assuming linear variation between east and p and west. So between the cell centroids, phi varies linearly, okay? That is not compulsory, but most of the general finite volume methods that are used in open source and commercial software, you assume it to linear because you get a smaller system, and as you make your cell size smaller and smaller, these linear variations would not affect your solution much unless you want a higher order accuracy, okay. The question is, the changes in the slope can only happen at the centroids. The values of phi are defined only at the cell centroids, right. So you can only define slope between the cell centroids, right. But if you want to define, let's say, a slope at the cell centroid, then there is nothing fixed. We will see how to calculate that, okay. Then you can use the phase values, interpolated phase values to calculate the value at the cell centroid and things like that, right. For example, so the thing is, you have up till now we have been only writing d phi dx on the phases, right, that is on the east, little e and little w, little e and little w. Now what if you were to get d phi dx at the p itself, right? We will see how this to be done. One way is to obviously use interpolate phi to the phases and then use those values and calculate it, okay. So these things we would not get it here, but whenever we get, we will come to that discussion, okay. Other questions? Fine, okay. We have kind of sidelined a little bit. I will go back to this. So where were we? Okay, so we have now linearized. We have introduced a linear model for our source term. So doesn't matter whatever would be the variation of the source term in terms of phi, we are always going to use this standard recipe, that is some constant. So this is a constant part, okay, and this sp would be a coefficient of the linear part, okay, which will multiply with phi p prime, that is not phi p prime, it is just phi p. I just have this phi to the power 1, okay. So where phi p is the value of phi at the cell centroid, okay. We have introduced linear model. Now will the linear model work? Will it give the same results? We are not discussing in today's lecture, we will do it little later, okay. Until then you would take this for granted. Alright, now okay, now let us go back and substitute all of these in the discrete equation, that is this equation, right, okay. So we are going to use this equation over and over. So I am going to plug all of these in, which will give me gamma east, A east times d phi dx east would be phi capital E minus phi capital P upon del x E minus gamma west, A west, d phi dx west would be phi P minus phi W upon del x W, okay. So that is what we have, the two terms. And then what else we have? We have the source term, that is plus S phi would be SC, that is some constant 10, 20 whatever, plus some SP, this is also a constant, it would be some 200, 300 whatever, times phi p, okay. So this is a model we have introduced for our S phi bar, okay. So that is a linearized model. What else we have? We have this multiplication with delta V equals 0. Okay, now if you take some books, maybe Westig and Malalsekara, it would probably include the delta V also as part of the S phi bar, okay. So they probably would introduce a model for S phi bar delta V, okay. For the entire thing they would introduce SC plus SP phi P. We are not doing that, we are only doing a linear model for S phi bar, okay. So that means we still have this delta V term hanging or multiplying our SC plus SP phi P, okay. SC and SP are constants within the cell. They could within the cell they are definitely constant. Within the entire domain they could be constant or they could vary depending on the kind of source terms you have. For example, you have put in heaters which will essentially produce, let us say, the same kind of heating capacity everywhere, then SC and SP would remain the same, okay. But the overall source term S bar would change, this would change depending on the location, because now you have a dependency on phi p, right. As a result that would change with phi p values, okay. But SC and SP most likely they will be kind of constant, or they could be functions of space as well, okay, depending on the problem. Alright, let us now rearrange all these terms. in a form that looks more appealing. So that would be, you would have collect all the coefficients for phi p, okay. Phi p coefficients are what? Are gamma east A east by delta xe with a minus. So we kind of send this to the right hand side. So that would be phi p times gamma east A east by del xe, and then we have another term here. This is minus gamma west A west by del xw with a minus here. We are sending it to the right hand side. This will be plus gamma west A west by del xw. Are there any other terms with sp, right? We have one more term which is multiplying phi p, that would become minus sp delta v, okay, equals, what do we have on the right hand side? On the left hand side now, essentially that would be phi east times gamma east A east by del xe plus phi w times gamma west A west by del xw plus what else? Sc, source term, the constant part, times delta v, right? That is what we have. Okay, now I kind of throw in another another thing in here. I will say that sp would always be less than or equal to 0, okay. I am kind of again stating this thing, okay. We already have a minus in front of sp, and I am saying the value of sp would be less than or equal to 0, okay. I am saying this would be in always or in most cases, okay. That means what will happen to the value of this entire term here, minus sp delta v. Delta v is always positive. What would be minus sp delta v? This will always come out to be positive, that is what I am trying to say. Now you may have a question, why not sp be positive, okay. That is for you to think and come back to me, otherwise we will discuss it later, okay. So this is for you to think why sp is not positive, and I say that it will always come out to be 0 or less than 0, okay, always negative or so, okay. Fine. So then let us write this in a little different way. So I would like to call these values in the parenthesis here, the curly braces, as some coefficient a, okay. So then this will be ap phi p equals a capital E phi capital E plus a west phi west plus b, okay. Now this is our discrete linear algebraic equation, okay. We will use only this form throughout the entire course. Does not matter whether you are looking at a diffusion equation or a convection diffusion or Navier-Stokes, anything, we will always, or an unsteady diffusion, we will always come back to this particular form, okay. So this is important. Alright, now what about the coefficients that we have? What about A east? A east is of course gamma east A east by del xe, right. If we go back here, this is our A east term, okay. Similarly, what would be our A west? Gamma west A west by del xw, that is, this is our A west, okay. Now what about AP? If you look at the coefficient, what does AP contain? A east, A west and minus sp delta v, okay. So that means we can write simply this as A east, okay, we can simply write this as A east plus A west minus sp times delta v, that is our AP, okay. Now what about B? B is sc times delta v, right. That is the only term remaining here. This is only sc times delta v, okay, very good. Now, okay, so now you see now if you go back to the discussion on Scarborough criteria, we had two things, right. We had an inequality and an equality, right. We said the summation modulus of A and B by modulus of AP should be less than or equal to 1 for all cells and should be at least less than 1 for one cell in the domain. That is what we said. Only then the convergence will be guaranteed. Now, it is somewhat easier to satisfy Scarborough criterion in inequality. Okay. So, this inequality satisfaction is sometimes not possible. Okay. That is where we have to look for. So, I will be using this equality and inequality. Okay. So, equality is, I mean by this equal to, inequality is this one, okay, or the other one appearing here. Now, with our discussion, we have to look for the coefficients AP, A East, A West, right. Essentially, we have to look for this guy and this guy for every cell in order to look for their magnitude to evaluate this Scarborough criteria, okay. Now, I also said that SP is negative, right. I said SP is negative, the source term. So, what would be now AP here? Sum of A, the neighbors, right, minus SP delta V. So, this is, does it satisfy, let us say if we have a non-zero source, right, we have a non-zero source, then does it satisfy Scarborough criteria? It does satisfy because it is greater than its neighbors by the amount of this minus SP delta V, right. If we have a non-zero source, yes. Gamma E or gamma W, can the diffusion coefficients be negative? The physical properties won't be negative, like viscosity, thermal conductivity, these are never negative, right, they are always positive, right. Delta X and the area magnitude, these are always positive, okay. So, so these can never be, these are always positive, okay, fine. So, it satisfies, if we have a non-zero source, Scarborough criteria is satisfied in what? In equality or in inequality? In inequality, okay. So, it satisfies in inequality. Now, if we have a zero source, let us say if we have a zero source term, then what will happen? It only satisfies in equality, okay, because then AP would be sum of sigma A and B or modulus of sigma A and B, then it only satisfies in equality. Then we have to look for some other sources where it could satisfy in inequality, okay. For all the interior cells, it only satisfies in equality. If we have a zero source term, only the equals is satisfied, not the less than condition. Fine, all right. So, by the way, where do we look for if it does not satisfy Scarborough in the interior cells? Boundary conditions, right. The source terms would, so essentially the source terms would help you make the system diagonally dominant, right, and the boundary conditions will also make the system diagonally dominant, right, because they will produce in this less than satisfaction, right, the inequality will be satisfied as well. Okay. Now, what boundary conditions satisfy, what boundary conditions do not satisfy, these things we will look into that, fine. So, essentially we have arrived at this equation and kind of finish the discussion. Now, essentially we write this kind of AP phi P equals A East phi East plus A West phi West plus B. So, this linear equation is what we have to write for every interior cell that we get, and we have to obtain a similar equation for all the boundary cells that we have, okay. Questions till now? Okay. So, we will come back to that essentially in a minute when we do the problem. Question? Yes. Yeah, it is probably not a function of E, it is just a, essentially that means it only satisfies inequality. Yeah, it could be a function of x, y as well, in which case it will not show up as a, in which case where will the source term be? The question is, what if the source term is only a function of x, y but not a function of phi, right, then where will you put this guy? Which term do you put this guy in? SC or SP? SC, right, because this does not depend on the dependent variable, it has to go into SC, right, it will become, it is only a function of the independent variables and it will go into the constant term, okay. Other questions? It will be actually, I think in the assignment it is a function of xy only, right, your assignment problem, okay. Other questions? Okay, fine. So, let us move on, let us do a simple 1D problem and try to formulate the system, and later on we will see how to solve it. Regarding the assignment, I am going to probably discuss it on Wednesday or so, okay, in the next lecture, just to kind of go through it in an overview so that you can probably solve it and answer your questions. Until then, I want you to take a look at it and understand how to solve it. Fine. We will have an overview of how to solve it on Wednesday or so, and we will move from there. Okay. Let us pick up a problem. So, let us say we have a 1D domain. Okay, we have a 1D rod or a beam on which the length is, let us say, 0.5 meters, and the boundary conditions are on the left end, which we call it as A, and the right end, which we call it as B. Left end, there is a heat flux given by QA. Okay, so this is known, a known heat flux QA, and the right hand side is maintained at a constant temperature TB. Okay, this is also known. Fine. Then the length is given. Let us say the thermal conductivity is 1000 watt per meter Kelvin, length is 0.5 meters, and the cross section area, okay, A is 0.01 meter square, and let us say the temperature TB is around 500 degrees Celsius, and the heat flux QA is, let us say, 1000 watt per meter square, and let us also introduce a source term. Okay, so there is a source term, S, and this S is given by let us say 500 minus 30 T. Okay, that is a linear source term. Essentially, your SC is 500, SP is minus 30. Okay, we have a source term as well that produces heat, generates heat in this beam. Okay, now the question is using finite volume method, discretize with 5 cells and obtain the temperature distribution at these 5 cells, okay, at these 5 discrete cell centroids T of xi. Okay, how do we do this? Okay, so essentially you have to use the 1D diffusion equation and then solve for this problem. Okay. Okay, so what is the governing equation? The governing equation is what? D by dx of k dt dx plus some s equals 0. Okay, this is a steady state problem. Let us say this is given in the problem statement. There is some steady state solution available. Okay, so we have d by dx of k dt dx plus s equals 0. Now, we will not do all the steps that we have done before. Okay, so I am going to kind of walk you through all the steps and write only the necessary one. Okay, so essentially what do? We integrate this on a control volume, change it to a surface integral, the volume integral to surface integral, then the surface integral has to be valued on the faces east and west, and we do all this and arrive at one equation, right? That is a equation of balance of fluxes with the source term. Okay, and that, if you recall, would look like Ka dt dx on the east minus Ka dt dx on the west plus Sc plus Sptp times delta V equals 0. Okay, so this is basically all the things we have done at the beginning of the lecture, and we have arrived at this particular equation. Do you all agree? Okay, are there any mistakes in this? This equation looks fine. Okay, fine. So we have now reached this one. Alright, then we have to also discretize our domain, right, which we have not done till now. So that is okay, looks pretty uniform. So we have this is first cell, second cell, third cell, fourth cell and fifth cell. What would be the width of each cell here? delta x would be 0.1, and the boundary conditions are also known. This is TB, this is QA. Okay, let's call this face as A, this face as A, and this face as B. Okay, A face and B face. Now we are still going to use the east-west phase notations for every cell. Okay, so the E and W, little e and little w, will be for that particular cell. Okay, I am not introducing all the faces here. Okay, now let's look at first the interior cells. We call 2, 3, 4 as interior cells, and we would like to call the fifth cell as a boundary cell, as well as the first cell as a boundary cell, meaning that these cells have at least one face common on the boundary. Okay, so first we can look at 2, 3 cells 2, 3, 4. Okay, so that is for cells 2, 3, 4. Okay, for the interior cells, we can again use linear profile assumption for temperature. Okay, and I can write one equation by collecting all the terms. I can come up with this linear algebraic equation, the discrete linear algebraic equation that will look like AP TP equals A east T east plus A west T west plus B. Okay, where you are going to tell me what would be A east. A east would be K east A east by del x E. Okay, in which case del x E equals 0.1, right? Del x E equals delta x equals 0.1. What would be A west? K west A west by del x W. What would be B? B would be SC times delta V, and AP would be A east plus A west minus SP times delta V, right? If we were to apply this to, let us say, cell 2, what would be the P? You would substitute P for 2, E for 3, right? East. For cell 2, east is 3 and west would be 1. Okay, so you would substitute these things, right? And essentially, do you know what is K? Right? K east equals K west equals constant, that is already given, 1000 watts per meter Kelvin. And we also know what is cross section area A, delta x is known, so A east equals A west equals A equals 0.01 meter square. What will be del x E? Del x W equals del x equals 0.1 meters. So everything is known. You can evaluate what is A east, A west, A P as well, because SC and SP are also known. You use all these values, okay, and plug in all these things back into this equation, right? You would get an equation in terms of what? T2, T1 and T3, right? Because you will replace what is TP, T east and TW. You will get an equation in terms of T1, T2, T3, right, for cell 2. Similarly, for cell 3 you can do the same, cell 4 you can do the same. Now what would change for cells 2, 3, 4 in these things, or which of these quantities will not change? K is a constant, A is a constant, delta x is constant, so the coefficients are not going to change, right? A east and A west are not going to change. Will AP change from cell to cell? Yes, AP changes because AP is a summation of A neighbors minus SP. SP changes because it depends on temperature. If source were also 0, then AP would also have been the same for all the 3 cells, okay? Okay, what about B? Would B change for cell to cell? For 2, 3, 4 it would not change because SC is constant, SC times delta V is the same, right? So you can think through and tell me that there are, essentially you will get 3 equations, okay, which would look something like, maybe the coefficients are completely wrong, but I would like to write it as 4T2 equals sum 3T1 plus 1T2 plus sum 10.5, okay. The coefficients are all incorrect, but you get some equation like this, right, and you get 2 more equations for T3 and T4, right, okay. These coefficients are of course not correct, I just wrote to indicate something, alright. You have now 3 equations for the interior cells, that is 2, 3, 4, fine. Okay, now we have to look at the boundary values, right, we have to look at the boundary values. Question still now. So we have 3 equations for the 3 cells, right, we just need 2 more equations. SP, so the question is, why not AP a constant for all the cells? Well, the thing is, yeah, I think AP will also be constant because SP is also constant here, right. If SP were a function of xy, it would be different, you are right. So, AP will also be the constant for all these things, right, because the TP is going into the unknown, right, it will also remain the same. So, AP also would be the same for all these three, correct. If it was a function of xy, like what Mane said before, then it would have been varying from cell to cell, okay. So, in your assignment problem it is different, no? Okay. So, let us look at the boundary cells, then let us look at the fifth cell first. So, this is cell 5, cell 5. So, cell 5, how does it look like? It looks like this. This is 5, this is constant temperature, and the neighbor is what? Neighboring cell is 4, and we have we call this as the faces are, we call this east and west, but we know that the east face is nothing but face B, okay, that is what we know. Now, what is our P? Our P is 5, right, P is 5, we are writing for this. Okay, we will go back and start off with our discrete equation, okay, that was what? K A dt dx east minus K A dt dx west plus SC plus SP TP times delta V equals 0, okay, that is what we have. Now, for the east face, if we were to calculate dt dx at east, that is dt dx at east would be dt dx at B would be what? Not 0. Why is it 0? It is an isothermal condition, right, it is not 0. Only thing is that we do not know the cell values for the E cell, right, we do not know what is the cell value for E, because we do not have such a cell here, right. If it were there, we would have calculated this as some T6 minus T5 by delta x, right, but do we have any other value? We have TB, right, I can do TB minus T5 to calculate the gradient, but what would be the distance between these two guys then? Delta x by 2, right, del x b by 2, okay. So, then this will be written as TB minus T5 by the distance would be del x e by 2, right. So, this would be the value for the gradient, okay. What would be the, for the west cell? dt dx for the west cell is what? It will be same as before, this will be Tp minus T west by del xw, that would remain the same, that means T5 minus T4 by delta x, okay, that is the same thing. Okay, fine, we will plug these in back here. This will give us K east A east times dt dx east would be this value, okay, that is Tb minus T5 by del x e by 2, okay. Let me write T5 as Tp, okay, this is Tp, okay, this is Tb minus Tp by del x e by 2, okay, and then minus K west A west times we have Tp minus Tw by del xw plus Sc plus Sp Tp times delta V equals 0, alright. Now, if you are to collect these terms, what do we get? You have a del x e by 2, this goes up, then this coefficient will become 2ka by delta x, right, from the denominator, okay. So, then what will be the coefficients for Tp? You send all the coefficients of Tp to the right hand side, you will get 2k east A east by del x e, right, because the denominator, the 2 half in the denominator goes to the top, plus we have K west A west by del xw minus Sp times delta V equals, what do we have on the right hand side, on the left hand side now from here? This would be T west times K west A west by del xw. What would be the coefficient for T east? T capital E? 0, we do not have anything, plus what about Tb? Tb has the same coefficient as that went into coefficient of Tp, that would be 2k east A east by del x e plus Sc times delta V. Do you all see this? Is this correct? right. Okay, if you were to call this as some coefficient A B, okay, then if we have a constant temperature, right, we have specified the temperature value, that is we have specified a what kind of boundary condition? Dirichlet boundary condition. Then what do we have? We have, if we have Dirichlet boundary condition on the east face, little e, what would be the coefficient A east? 0. What will be the coefficient A west? Remain the same, Kw remains the same, Lxw. What will be the coefficient AP? Aw minus Sp delta V plus this guy, which is nothing but AB. What about the coefficient, what about the value for B? Now Sc delta V was B till now. What about TB? Is TB known? TB is known, right? What about this coefficient? Is it known? So where will this guy go? As an unknown or known? This will be an unknown. So where should be this put up in? As part of B, right? This will be part of B. So B would be Sc delta V, that is what we had till now, plus what else? AB times TB, right? AB times TB. So what have we done? What we have done is essentially we have cut off the link to the east cell, right? By setting that coefficient equal to 0, right? By setting this to be equal to 0, we have cut the link to east cell because we don't have an east cell for the boundary phase 5, right? And included the other contribution that is coming from the phase into the AB value, that is into B as well as into AP, okay. Now I will kind of finish up here. Now what is AP here? AP is A west, right, plus we have AB minus Sp delta V, right. Now does it satisfy Scarborough? For the fifth cell, how many neighbors are there? Only one neighbor, right? 4 is the only neighbor, right? A west is the only neighbor. So AP should be equal to A west, right? But in addition, we have what else? We have of course AB and we have a source term. Of course, let us say we have a 0 source term. We have a 0 source, then does it still satisfy Scarborough or not? It will still satisfy because it is now higher than its neighbors by a value of AB, right. So it still satisfies Scarborough in inequality even if we have a 0 source term. Now this is happening because of the type of the boundary condition that we have, which is a Dirichlet boundary condition, okay. So if we have a Dirichlet boundary condition, it will help you satisfy Scarborough criteria in inequality, okay. We will look at this again later on in the 2-dimensional problems as well. So I am going to stop here. We will pick up the heat flux boundary condition in tomorrow's lecture, fine. Okay, thank you.